Welcome to the Week 7 Math Prepare. So this is a question about joint and conditional probability distributions and their properties. To help you with this question, we'll review the definitions of a probability distribution function, joint distribution, and conditional distribution. So a probability density function, written this way, right here, describes a relatively likelihood of x taking on a particular value. Sometimes you'll see the random variable dropped in our notation when it's clear what random variable we're talking about. So here, if it's clear that a random variable is x, we might just write p of x when we really mean probability of my random variable being the value x. If x is discrete, then this probability distribution here, probability of x or p of x, that describes the probability that my random variable takes on a particular value. If x is continuous, then we integrate over a range of x's to obtain the probability of the random variable x taking on a value within this range. So other properties that we talked about earlier include that these probability distributions are always positive, and if we either sum over the possible values or integrate over the possible values, we're going to get 1. So this is in the discrete case. This one is in the continuous case. So a joint distribution describes the likelihood of a pair of variables, random variables, taking on some values. So this is shorthand for probability that my random variable x is x and my random variable y takes on the value little y. So joint distributions are distributions. So if we integrate over the possible values, we should get the number 1. So this is in the continuous case. In the discrete case, we get something similar where if we add up all the possible values for my random variable x and my random variable y, I should get 1. Also, we can get back our probability of a single random variable. So this is a probability that x, my random variable x is little x, and my y could be anything, right? Because I'm not specifying a value of y here. And well, the way we find that is we can use the joint distribution, which gives us the probability that x takes on a certain value and y takes on this value. And we can marginalize over y. So we could sum or integrate over the possible values of y. And that should give us back, well, what is the probability that my random variable x is just little x and y could be anything. A conditional distribution, like this one, describes the likelihood of y taking on some value conditioned on the fact that my x random variable takes on the value little x. So another way to write this is probability that my random variable y is a value little y, given that my random variable x is this little x. So conditional distributions are distributions over y. So we still have this property. We also have the property that probability of y given x is always positive. There is also this property called the chain rule, unrelated to the chain rule in calculus. So this chain rule says that the probability that my x is this value little x and my random variable y is this little y, well, that is the product of I'm going to write it this way. Probability that my big X, my random variable X, takes on that value. And so multiplication here, right? And my Y takes on Y given that, that I'm in the situation that my random variable X is this little x. So what I've written down here is the same as what is written down here, just slightly simplified notation down here. And I could write it, rewrite the joint distribution this way as well. I'm just flipping x and y here. So I could choose my value of y first, and then my value of x conditioned on y. Finally, putting this together, we have the Bayes rule, which really just comes from this part right here, where if I just isolate probability of y given x, well, that's really just this probability right here. So I'm just moving, moving this part down to the denominator. And we are going to be using the Bayes rule a lot in maybe not the coming lecture, but a couple lectures from now.